my wife and I just had some ceiling fans put in a couple rooms of our house. Um, the guest bedroom, the kitchen, the laundry room. The reason I bring that up, this is not a flower. It's a rough drawing of a ceiling fan with 5 blades. And a ceiling fan works, this is not news to you, but a ceiling fan works by rotating. Rotating around its center. Around an axis through its center. As opposed to rotating around an axis through any other point. I have a good way to illustrate the difference. Here's a lid to a jar. And if we're interested in rotating around an axis through the center, then we just have to turn it. If we're interested in rotating around some other point, then the rotation looks a little bit different. That's all. Very good. So, this is an object that is arguably symmetric. If we were to calculate its center of mass, I think we would always get an answer of that blue dot. These two blades basically counteract each other. They're on almost opposite sides of the fan, so the left-right center of mass is in the middle. They're both a little bit farther up than the center, but these two blades are quite a bit further down, and they would drag the center of mass down further. Again, they're symmetric on either side, so the center is still somewhere on, I guess, a center line. The combination of this blade on center and these two help to put the center of mass in the middle at the actual center. So as this rotates, what is the velocity of the center of mass? The answer is 0. The center of mass isn't moving, it stays put. So what's the kinetic energy of the fan? Its velocity is 0. So its kinetic energy is 0? Which doesn't make any sense. It's moving, right? It's got to have, there's mass here that's moving. I don't know, how can its velocity be 0? I mean, it's definitely moving. If you put your hand up there and it'll hit your hand and it'll hurt because, you know, I don't, because, and the difficulty is that the motion that we've been discussing doesn't do a good job of describing this. Chapters 9 and 10 are about the rotational motion of what I'll call rigid bodies, bodies whose orientation with respect to themselves don't change. Different from the rotation of a I don't know, a floppy frisbee dog toy kind of thing, or different than the motion of a Kleenex, of a facial tissue. If we throw it with respect to itself, it can deform and change shape relative to its original shape. And that's not the kind of motion we're talking about. We are talking about the motion of rigid objects whose, if I toss this across the room, nothing happens to its shape with respect to itself. It just moves or rotates in this case. So we'd like to develop a kinematics for this kind of motion. Okay. Suppose that this inner hub has some small radius r, and that the fan blades have some larger radius, capital R. It takes some amount of time for the fan to rotate. I don't know how much time. But we talked a little bit about the time that it takes to make one full rotation. We called that the period back when we were talking about centripetal motion. And I'm just going to call that capital T for now. I don't know how much time it is, but it's that much time. In a time, capital T, this point here on the hub, right at the end of that radius that I drew, will describe a circular path. That point will move around the hub and get back to where it was. So if we asked for the average speed of that point on the edge of the hub, B hub, we know that it travels a distance according to the circumference. In an amount of time, capital T. But if we do the same calculation, that point on the edge of the blade makes a much larger circle in the same amount of time, capital T. And the fact that these are not equal speeds is confusing to me. I mean, I was with you. We said, okay, its velocity can't be zero. Well, it is, but it isn't. Okay, I guess I was already confused, if I'm being honest. The velocity of the center of mass of the fan is zero, but it is moving. Not only that, but different pieces of it are moving at different speeds. Yeah, so what, it's tearing itself apart? How is one piece of the thing moving faster than the other piece? I don't understand. They're connected, right? Like, it's not that the blades are doing something and the hub is doing something else. It's all connected. So what is the deal? And again, the problem is that these definitions work for linear motion. They're not built for rotational motion like this. That doesn't stop these things from being true. It just stops them from being useful. If we do this calculation for the center of mass of the blade, or I'm sorry, of the whole fan, The answer is 0, because its center of mass isn't moving at all. What is true about every point? Every bit of this ceiling fan is rotating such that it describes a full rotation in time t. So all the points of the fan rotate one full rotation in time t. One full rotation isn't the only way I have to talk about this. One full rotation is 360 degrees, or 2 pi radians. So we could, if we want to, make up a definition, rotation rate. How much rotation per time? And we could do the calculation. It would be 2 pi radians. I'll just write rad. 2 pi radians divided by time t. The rate at which angle is swept, I guess, is rotated through. Okay. Okay, all right. I'm just trying to chase through some of the consequences of this new thing. So we used to say that the rate of linear motion, the linear motion rate, was velocity. Linear motion rate was displacement over time. That's how we defined it. We didn't call it linear motion rate, we called it velocity, but that's what it is. And here we are talking about a rotational motion rate. And we've said that it should be, I mean, I guess this is true for a full period, but what is it? Two pi radians is the amount by which the angular orientation of the fan has changed. See, because, all right, I'm gonna draw a really quick version. If we only let it go for half the time, if we only let it go for half a period, it ends up upside down. The angular orientation has changed by pi radians. So this is scalable according to how much time goes by, and wait, so like sweeping through, I don't know, but this point here has moved here, and has therefore rotated through 180 degrees or pi radians. So its angular orientation has changed from this to that, which is pi radians. It's a rotation about the center of 180 degrees. How much do we rotate by in how much time? Because every point on the fan has an angular orientation that changes by exactly that amount, right? This point here, I'll use a different mark. That point, the end of that blade, rotates from there to there 180 degrees in the same amount of time, period over 2. So I think this is what we're talking about. How much has the angular orientation, theta, of a particular point on the body, on the object, changed in how much time? How much has the linear orientation of an object changed over time? We're asking a very similar question, but we're just applying it to a kind of a different motion that looks different. The overall position of this object isn't changing, but its orientation is. Cool. Let's put the actual names back on this stuff. Linear motion rate we call velocity. And rotational motion rate now that we're here in chapter 9, I'm going to define that as an angular velocity. Angular because we're talking about angles, velocity because it's a rate of change over time. Which makes me think that we could define an angular position just like we defined a linear position. Well, yeah, I mean, it's the angular orientation we have relative to some axis. Let's track that with variable theta. Could be a function, changes in time. We're about to say that. A function in time. I mean, you can see where I'm going, right? We can see the calculus coming a mile away. Okay, angular displacement. Sure, why not? Theta at some later time minus theta at some earlier time, just like we defined regular linear displacement. Position now minus position then. It's the same thing, it's just angular position. So, okay, fine. We'll call that delta theta. And that's what we're talking about here. Displacement over time. Well, angular displacement over time. So we've got symbols for these guys. These are expressed in what? This is radians. So is this. And if we stick with our metric, we're measuring time in seconds. So this thing has the dimension of, or the unit of radians per second. How many radians has the angular position changed in how much time? Cool. We need a symbol for this new animal, angular velocity. the symbol I'd like to use for it, well, yeah, the symbol I'd like to use for it is the Nationals logo. It's a lowercase Greek letter omega. It looks like a lowercase cursive W, sort of curly, you know, like cursive is. But on the when I'm drawing it, I'll make sure that it has the center loop like a pretzel kind of, so that it doesn't look like a W. So this is omega, and I hesitated a minute ago. If we're talking about delta theta over delta t macroscopic changes, we're actually talking about the average angular velocity. So we've got our omega average. Just like we had our v average when we initially defined velocity. So this is average velocity. But we do that. Okay, cool. The fact that everything is proceeding in a very similar way, right? So we had displacement over time is velocity. Here we're talking angle, but displacement over time is velocity. Displacement over interval time is average velocity, average angular velocity. The fact that the definitions look the same makes me think that I could take the limit as delta t goes to 0 and talk about a derivative just as well as we used to. So if you wanted instantaneous angular velocity as a function of time, then you could take the derivative of the theta. Angular position. Time rate of change of position, that's velocity, just angular. And it makes me think that we could define an angular acceleration just like we defined a linear acceleration. We let the angular velocity change in some amount of time, and we're talking about an average angular acceleration. This will have the unit of radians per second or radians per second squared. And the symbol I'd like to use is alpha. This is not the proportional symbol. That is a little bit different. Looks more like that. I'm not very good at drawing it, frankly. That's better. Is proportional to, that's that. It's wider, kind of shorter. This is alpha. It's a little bit narrower and kind of taller relative, anyway, you know what I'm talking about. This is an average because we're talking about delta. If you want to talk about instantaneous, we can do that too. Put it over here in this color. If we let delta t go to 0, what we end up with is a derivative, and we're saying that alpha as a function of time is the time derivative of the angular velocity. The great thing about this is that once we have defined the way that we're going to keep track of angular position, the rest of it just kind of falls like dominoes because we already know how position and velocity are related and how velocity and acceleration are related. It's just we're tracking a different kind of position, that's all. So all the math is going to turn out pretty much the same. Again, it's just we're describing rotation instead of, linear motion through space. In fact, now that I've said that out loud, that makes me think, wait a beat and let this, and then I'm going to erase it. At least some of it. We used to have constant acceleration kinematic equations. We had, let's see, V is V0 plus AT, delta X is V0T plus 1 half AT squared, V squared is V0 squared plus 2A delta X, and V average is equal to the sum over 2. The definitions we just made for theta, omega, and alpha are identical to the definitions we made for X, V, and A. Do calculus with a constant alpha. We will end up with exactly the same relationships as we had for a constant acceleration, just written with angular variables. They're the same equations because they're the same relationships. Again, we're just describing a different kind of motion. These equations result from the calculus, from the definitions that we make, and we made exactly the same ones. So there's no accident that these equations are, at least as far as calculus, identical to these. We're just using them, again, to describe a different kind of motion. That's all. So they look a little bit strange because they're using different variables and we're not used to looking at these variables, but they are, in fact, equations, relationships that we're very familiar with. Displacement is equal to initial velocity times the time plus 1/2 times the acceleration times the time. Displacement is equal to initial velocity times the time plus 1/2 times the acceleration times the time squared. That's the same stuff. Just here we're talking about angular displacements, angular accelerations. Cool. None of this can take away from the fact that I know this stuff to still be true, though. That the actual speed of a point on the hub is less than the actual speed of a point on the blade. And that's weird still. I mean, okay, they all rotate at the same omega, I guess. But how do we sort of translate that to the fact that apparently these speeds are different? It's like, sure, you know, you can measure things differently, you can talk about rotation, but at a certain point, it still has to be true that that point on the end of the fan blade describes a circle of a particular circumference, and it needs to go that far in time, capital T. Like that I don't have a choice there. That's just true, and that means that 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 point on the end of the fan blade has a greater speed than this one because it's describing a smaller circle, and the difference is the radius. The difference is the radius. Wait a minute. Hold on. What did you? The rotating fan, right? It made one full rotation, 2 pi radians every time t. So we wrote earlier that omega, let me do this in a different color, that the angular, the rotational motion rate, delta theta over delta t, omega, the angular velocity of the ceiling fan is 2 pi radians per time t. So I'm just radians per second. Two pi over time, 2 pi over the period, times the radius, the distance of the point that we're talking about away from the axis around which we're rotating. Let me draw the quick picture again. Let me draw the whole thing. There's one fan blade, and there's 2 fan blades, and there's the, okay. So the inner radius, R, outer radius, capital R. If we're talking about this point on the end of the fan blade, we do this calculation, and the result we get for the linear speed, the distance traveled divided by the time we took to do it, this is distance traveled in meters, divided by the time we took to do it, is just this times the radius of the circle we're talking about. And the same story here. If we're talking about this point on the edge of the hub, 2 pi over t, so we take omega and multiply by the radius of the circular motion that that point is following. How far away is that point from the axis about which we're rotating the center of the fan? Okay, and the last piece. The center of mass of the fan is that center point. It's the same point as the point of the axis around which we're rotating. So if I'm going to follow the pattern, I take 2 pi over t, 2 pi over t, I take 2 pi over t, and then I multiply by how far away that point is from the axis, 0. So call me crazy, but it looks to me like if I want the linear speed, I can take omega and multiply by r. I'm going to use the lowercase r because it could change. We could use any point from the center all the way out. I don't have to use capital R, so I'm just, could be talking about any old radius multiplied by omega. That gets us, no, wait a minute. Omega is radians per second. R is in meters. And velocity, actual linear speed, should be meters per second. What happened to radians? Nothing happened to it. It was never really there to begin with. We've seen this trick before, actually, this disappearing act of the unit radians. Talking about arc length. The arc length is in meters. It's a length, the distance. The angle is in radians. And the radius is in meters. It's a length. We never had a problem with that before. Circumference, 2 pi r, 2 pi radians, radius r, and radius is meters, circumference is meters, 2 pi radians, and the radians just disappear. How do they do that? Pi is the number that is the ratio of a circle's circumference to its diameter. Both are lengths. Pi is dimensionless. It has no dimension. It's just a number. It's the ratio of two lengths. But when we talk about angle around a circle, we're just counting. We're how many, we give it a little marker to indicate that we're talking roughly about something circular or something rotating, something angular, but there's not really a unit there. When we express omega, we leave radians per second because we are counting dimensionless things over time. So we leave the marker, we're counting dimensionless things. As soon as we multiply by meters, now we've got a dimensional thing. We've got a thing that has dimension, so let's leave that. We don't need the dimensionless marker anymore because we're talking about something real, quote unquote. Not that radians are fake, just that they have no dimension. They don't have the unit of length or whatever. Angle is a dimensionless quantity. We're talking about radians per second. Again, we leave the marker, radians, just so that we know what we're talking about. But then as soon as we have something that is dimensional, we let the radians go away. We don't need the marker anymore. Excellent. So we have rotational well, you know what? If I can do this trick, and everything else seems to line up really well, I don't see why this shouldn't line up really well also. Maybe it's true that the acceleration is alpha r. This is A, this is alpha. Certainly seems to follow the pattern. So we have all of these rotational kinematic variables and all of these linear kinematic variables, and we can hop back and forth between rotational and linear. This is great. Except the velocity, the acceleration, these are vector quantities. If the left-hand side is a vector, the right-hand side needs to be a vector. But if we're going to get vector content from the right-hand side, where does it come from? And that's what the next segment will be about.